the last thing I taught you about Peano axioms. Today we're going to use them to prove some stuff. And especially we're going to do our first examples of mathematical induction. But before that, I want to prove something for you using these axioms, which is very profound. We want to prove that 2 + 2 is 4. Amazing. So, but before we do that, we have to define some things. We have to define what 2 is, we have to define what 4 is, but more importantly, we have to define what we mean by plus. Right? Because remember, we have Peano's axioms, and they basically just give us a definition of what natural numbers are. And the way they worked was that I have something called 0, and for every number, I have a successor. Right? Well, defining 2 and 4 and so on is not that hard, because that's basically human language for some of the expressions that we get if we use Peano's axioms. So, for example, the successor of 0 is what we call 1. The successor of 1 or the successor of 0 is what we call 2, and so on. So if I want to prove that 2 + 2 is 4, actually what I want to prove is this. Successor of 0 plus successor of 0 is, okay, I'm not going to put the parentheses anymore. It's this. Right. Okay. So this is what we normally call 2 as humans, and this is what we call 4. But there are 2 remaining points. One point is, what does equality mean? But that was those 4 axioms that I said. Don't think about them for now. But the more important thing is, what does it mean to do addition? So we have to somehow give a definition of what we mean by addition. And this is going to be our first example of a recursive definition. So I'm going to give you a definition that kind of uses the 5th axiom. So definition of addition. I say that addition is an operator that takes 2 natural numbers and gives me another natural number. So it's just a function that gets 2 natural numbers, gives me another one. But I have to have some rules for how addition works. And these are my rules of addition. So rule number 1 is that I say for every natural number n, and I write for every n, I don't specify the universe here. My universe is the universe of natural numbers. So for every natural number n, n plus 0 is n. Okay. And my second rule is this. I say for every 2 natural numbers n and m, n plus the successor of m is the successor of n plus m. Do you see why this defines addition for every pair of numbers? Because when we were talking about Peano's axioms, we said that we had 2 ways of creating natural numbers. One way was that 0 is a natural number. The other way was that if I have a natural number, its successor is also a natural number. Right? So I'm defining how I can add 0, and I'm also defining how I can add a natural number that is the successor of something else. So this defines addition for all possibilities. So this is what addition means. Of course, again, this is not how we do addition in real life, but this is how we can define it, and then we can mathematically reason about it. Okay. So using this definition, well, this is kind of a hard theorem. Maybe let's start with something easier. Let's prove 1 + 1 is 2. Okay. So 1 was the successor of 0, and this 1 is also the successor of 0. So I want to find successor of 0 plus successor of 0. Okay. Now, which one of these rules can I apply? I can apply the second rule. So I can say that this whole thing is the successor of 0 plus 0. Okay. But now I can apply rule 1, and I can say that successor of 0 plus 0 is just successor of 0. So this whole thing is equal to successor of 0, which is what we call 2. Okay. Now let's go back to 2 plus 2 is 4. This is exactly the same thing. It's just a little bit longer. So this is what I have. I have successor of 0. Again, I'm going to write it without the parentheses because it's just too hard. Successor of 0 plus successor of 0. Okay. What is this equal to? So first I say that my second number is the successor of something. So my whole sum is the successor of the sum of the first number and whatever I had here. Okay. But then I have to apply the same rule again because my second number is still the successor of something. So I say this is the successor of 0 plus 0. And at this point, I have plus 0. So I can apply rule 1 and I can basically remove the plus 0. So I get this, which is 4. So this is a proof that 2 plus 2 is equal to 4. Okay. So this is the first thing that we wanted to do using Peano's axioms. But now I have defined addition. How can I define multiplication? I can also give a recursive definition for multiplication. Right. So let's do that. Let's do definition of what it means to multiply two numbers. Again, I can just give two rules. Rule number 1 is that I say for every n times 0 is 0. And my rule number 2 is that for every n and m, I have to say what happens if I multiply n by the successor of m. Okay, but I already have addition, so I can use addition here. I can say this is just n times m plus n. Plus n. Okay, yeah, so this is how I can define multiplication. I will give you a homework where you have to define division. Okay. But now we want to go back to the mathematical induction. So let's write this here. So mathematical induction is this proof idea that we want to use the fifth axiom of Peano to prove that something holds for all natural numbers. So the idea is this: if you want to show that, let's say, phi of n holds for all n, so phi of n holds for all natural numbers n, you do two things. It's sufficient to show these two things. So I want to show that some property phi holds for every natural number. If I show that phi holds for 0, and then I show that for every natural number n, if phi holds for n, then phi also holds for n plus 1, that's enough to show that phi holds for all of the natural numbers. And again, this is the last axiom of Peano. So I first show that phi of 0 holds. And then I show that for every natural number n, if phi of n holds, then phi of n plus 1. Now, to be honest, it's a little bit strange that in Peano's axioms, we're starting our natural numbers with 0. We can also start our natural numbers with 1, right? And if I do that, then the only thing that changes here is that I have to show that phi of 1 holds, and then for every natural number greater than or equal to 1, if phi of n holds, then phi of n plus 1 holds, right? So I can do that too, but I just used the word here that I haven't defined. I said for every natural number greater than or equal to 1. So let's define that too. How do we actually compare two natural numbers? Based on what we have so far. So when can I say that n is less than or equal to m? So say definition of less than or equal. I say for any two natural numbers n and m, n is less than or equal to m, if and only if what? How should I define this? Well, here's a trick I can use. I can say if there exists another number that I can add to n, and that would give me n. So if there exists some x, and again, my universe is natural numbers, such that n plus x is m. Because I have addition, I can use addition in the definition of comparison. Now, there are better ways of defining this too, I mean, subjectively, but this is one way that will define it. Okay. But let's actually see some examples of using mathematical induction. And sometimes we start with 0, sometimes we start with 1, depending on the problem that we're working with. So here's the most classical example, like every textbook that introduces mathematical induction starts with this example. So this is, and let's say problem 1, prove that the sum of the first n numbers, 1 plus 2, so on to n, is equal to n times n plus 1 over 2. Okay. Now, in this course, we want to be a little bit more formal and write this like this. Okay. Great. So if I want to prove this, I have to prove that it holds for, so I want to prove that this holds for every value of n. Now, does it make sense for n equal to 0? Well, if you look at this way of writing it, it might not make sense for n equal to 0. And then you might say, well, I just want to prove it for n's that are at least 1. But if you look at this form of writing it, it makes sense even for n equal to 0, and it's just 0. Okay. So I want to prove that this holds for all n in n. Okay. So I'm going to do two things. And by the way, let me give these things names. So I call this the induction basis. And I call this second one the induction or inductive step. Okay. So let me prove the basis first. The basis is super easy. If n is 0, the left side is 0, and the right side is also 0. 0 is equal to 0. Okay. So the base case or the basis case is very easy. 0 is equal to 0. I'm happy with this.
Okay. Why is the sigma notation defined when n is 0?
Oh, so think of the sigma notation like a for loop. If you have a for and it says for I from 1, so okay, think of it like this. Think of it like a C++ for loop. Let's say it's for I equal to 1, I less than or equal to n plus I, do something, basically add I, right? And what happens if my n is 0? This for loop just doesn't execute. So my sum would just be 0. Yeah. Okay, so that's my base case. Or alternatively, if you want to start from 1, you can say that my base case is that, well, 1 is equal to 1 times 2 over 2, which is, of course, 1. This is fine. Okay, now I want to do the induction step. So here's the thing. What do I want to prove in my induction step? If I want to be very specific about what this is, I want to say that for every natural number n, if this statement holds for n, then this statement holds for n plus 1. So for every natural number n, if 1 plus 2, so on to n is equal to n times n plus 1 over 2, then if I do the same sum, but go all the way to n plus 1, this is equal to n plus 1 times n plus 2 over 2. But this is great, because now I have to prove an implication. And because I have to prove an implication, I can just assume the left-hand side and then use it to prove the right-hand side. Okay, so let's try this. So I can assume that the left side holds. So this is my assumption. And I want to prove that the right side holds. So this is my goal. This is what I want. Okay. But let's just look at this right-hand side, or actually left-hand side of the right expression. 1, 2, 3, so on, plus n plus 1. Okay. What is this equal to? Well, I can look at this first part. And according to my assumption, this first part is n times n plus 1 over 2. Okay, so I can just replace it. I can say this is n times n plus 1 over 2 plus n plus 1. Okay, so I just multiply this by 2 and put it there. So I will get n plus 2 times n plus 1 over 2, which is exactly what I wanted. But the other. Okay. So this is the induction step. Having that assumption, I could get to this goal. So basically, assuming that the property holds for n, I could prove that the property holds for n plus 1. So the property holds for 0, and whenever it holds for n, it holds for n plus 1, so it holds for all natural numbers. Okay. This is basically what we call induction. But now I'm going to give you some other rules, or let's say proof techniques, that are actually equivalent to induction. And then we're going to use them on this example and also some other simple examples to see why they're basically doing the same thing. Okay. So the first thing I want to tell you about is the well-ordering principle. This is a very simple statement. It just says that if I take any set of natural numbers, and if my set is non-empty, then it has a minimum element. It has a smallest element. Okay. So every subset, let's call it A, of the natural numbers that is not empty. So okay, every non-empty subset A of the natural numbers has a smallest element. What does the smallest element mean? Well, we have already defined this one, we have already defined less than or equal, so I can actually compare elements, right? So the smallest element or the minimum element is an element of this set that is less than or equal to every other element of the set. So the well-ordering principle says that if you take a non-empty subset of the natural numbers, this non-empty subset definitely has one smallest element. Okay. Now, here's the part where things get interesting. I claim that this is actually equivalent to induction. So the axiom of induction and well-ordering, they're saying the same thing. Okay. But for now, I don't want to prove it yet because I want to give you another way of saying the same thing. I want to show you some examples, and then these examples will give you the intuition for why these things are equal. And then after the examples, I will actually come back and prove that they are all equivalent. Okay. So the next one is what we call the infinite descent principle. And basically it says this. It says I cannot have a sequence of natural numbers that is both infinite and decreasing. Okay. So it says there is no sequence, there is no infinite sequence let's call it A1, A2, so on, of natural numbers such that A1 is bigger than A2 and A2 is bigger than A3 and so on. Okay. To be more specific, if I want to write this, I would say that such that for every I, AI is bigger than AI plus 1. So I cannot have an infinite sequence of natural numbers such that it just gets smaller and smaller as I'm going. Okay. Again, very importantly, we're talking about natural numbers here. If I was talking about integers, I can, of course, have such sequences. I don't have negative numbers here. Okay. So let's see some proofs that actually use these principles. By the way, this is called the infinite descent principle, but actually it's saying that infinite descent is impossible. Right? So the naming is not great. Let's do this. Oh, by the way, in this course, I'm going to use a lot of things that you have seen before, but we have not formally defined. And I'm just going to assume that we have the same understanding of them. But then at some point in the course, I will come back and define them. So right now, I'm using real numbers and rational numbers and so on, but we haven't defined them yet. I will define them at some point, but let's just use it anyway. So this is the second problem I want you to consider. This is problem 2. I want to prove that square root of 2 is irrational. Okay. So basically, I want to show that I cannot write square root of 2 as a fraction where the numerator and the denominator are both natural numbers. Okay. Now, I want to prove this using this infinite descent principle. Okay, how do I do this? So I first do a proof by contradiction. So this is my proof. I want to say, suppose that there are two natural numbers, A and B, and of course B is non-zero, such that square root of 2 is A over B. Okay. So what can I do with this information? I know that square root of 2 is A over B. So I can just square both sides. So I'll get that 2 is A squared over B squared. Okay. But what does this tell me? This tells me that a squared is 2b squared, which means that a squared is actually even. Okay. But here's the thing, when can a squared be even? A squared can be even only when a itself is even, right? So you can prove this on the side, that if a is odd, then a squared is also odd. So if a squared is even, then a must be even. Okay. So at this point, what I know is that a is even. Okay. But if a is even, that means that I can write a as 2 times something else. Okay. So I can say that there exists some other number, let's call it c, such that a is equal to 2 times c. Okay. But if I do that, then let's go back here. So what is a squared? It's 2c, all of it squared, so it's 4c squared. Right? And 4c squared is equal to 2b squared. Now I can cancel 2 from both sides, and I can get that 2c squared is b squared. Oh, look at this. B squared is now even. And if b squared is even, that means that b is even. Right? So this is even, and then b is even. Okay, so what does that mean? That means that there exists some other number, let's call it d, such that b is 2d. Okay. Now, let's go back to the very beginning. Square root of 2 is a over b. Okay. So square root of 2 is a over b. But a was 2c and b was 2d. So square root of 2 is 2c over 2d. Now I can cancel the 2's. I can get that this is c over d. Okay. Now, this looks pointless up until this point, until you realize what's happening here. So I had a way of writing square root of 2 as a fraction, a over b. But now I found a different way of writing square root of 2 as a fraction, c over d. But importantly, if you look at the numerator here, the numerator is decreasing. C is only half of a, right? And I can continue the same thing. I can just do whatever I did here with c over d and get another fraction with an even smaller numerator. And I can keep doing this. Now, this will give me an infinite sequence of natural numbers. And this is a decreasing infinite sequence of natural numbers. Now, the principle of infinite descent says that this is not possible. So square root of 2 cannot be written as a over b in the first place. Okay. Now, this is one proof, but let's now do the same proof, but let's do it using the well-ordering principle. Oh, and by the way, here I'm actually getting 2 infinite decreasing sequences of natural numbers, right? Because I can also look at the denominator, and the denominator is also always being divided by 2. Okay. Well, there is one more thing that we haven't technically proven, but you can prove it yourself, and that's that every number is smaller than twice itself. Right? You have to prove that, other than 0. So here, I know that's, well, I forgot to write that a is also not 0. Okay. Now, let's try to prove the same thing using the well-ordering principle. So remember, the well-ordering principle says that every non-empty subset of natural numbers has the smallest element. Okay. How would I prove the same thing using this principle? Well, I can say, suppose that I look at the set of all the numbers that can be the numerator here. So I say, suppose my set A is basically the set of all natural numbers A, such that there exists a B where square root of 2 is equal to A over B. Okay. I want to prove that this set is empty, because basically I want to prove that it's impossible to write square root of 2 as A over B, where A and B are natural numbers. Okay. Now, again, I do proof by contradiction. I say, suppose this set is not empty. If this particular set is not empty, then according to the well-ordering principle, it must have a smallest element. Okay. So now I say take its smallest possible element. And you see where this is going. So I'm saying write square root of 2 as A over B, but choose this A to be the smallest possible A. Okay. And then do exactly the same thing that I did here. But then this gives me a way of writing it with an even smaller denominator. But this is a contradiction because my original A was supposed to be the smallest possible numerator. And then now, sorry, not denominator, numerator. So, and now I have C, which is even smaller. Okay. So I hope that by this example, you kind of see that these two are saying the same thing. Right? So in one case, what I'm saying is, well, I find a solution and then I find an even smaller solution and keep doing the same thing. And I say, I cannot do this forever. I cannot forever find smaller and smaller solutions. In the other proof, I'm saying, look at the smallest solution in the first place. And if I can find anything that is smaller than that, it's a contradiction. Let's do another one. So this is our third problem. Let's do this. There are infinitely many prime numbers. Again, I'm assuming that you know what prime numbers are. I want to prove that there are infinitely many prime numbers. Okay. How would you prove this?
Usually the largest line.
Okay. But we have a problem with that. I cannot talk about the largest prime number, right? Because what I have here so far is that if I have a non-empty subset, I can talk about its smallest element. Okay. So actually, in this case, the set that we're going to create is a very simple set, so we can just know what the smallest element is. So we can say, again, let's do a proof by contradiction, and let's suppose that I have finitely many prime numbers. Okay, so let's P1, P2 to Pn be all the prime numbers. Okay. I'm going to look at the set of all the numbers that are bigger than the product of these prime numbers, and I'm going to look at the smallest number there. But in this case, because the set is so easy to define, I can just immediately say what the number is. I want to look at this number, P1 times P2, so on, times Pn plus 1. Or basically the product of all the PIs, I from 1 to n plus 1. Now, I claim that this number k is either prime itself or has a prime factor that is not listed here, that is not one of P1 to P. Okay. So first of all, if k is a prime itself, then well, I've already found the contradiction that I was looking for, because k is definitely bigger than all the primes that I've listed here. So these were not all the primes. But let's say that k is not a prime. So that means that I can write k as some factorization a times b, where a and b are not 1 and they're also not k. Okay. Now, here's the thing. What happens to a and b themselves? Can a be one of these prime numbers that I've listed here? No.
No.
Because you can easily see that if I divide k by any of these prime numbers that I've listed here, it's going to have a remainder of 1, right? But k is a multiple of a. So if I divide k by a, I'm going to get a remainder of 0. So it's impossible that a is one of these prime numbers. Okay. But now I can continue the same argument with a. I can say, look at a. Either a is a prime number itself, in which case I have found a prime number that was not in my list, or a can be written as some product of two other numbers. So let's call this one a1 times b1, right? And then I can say the same thing. I can say, well, look at a1. Can it be one of these prime numbers? No. So now a1 itself, it's either a prime number, in which case I found a new prime number, or I can again factorize a1, right? But now here's the part where I'm going to use this infinite descent principle. I cannot keep doing this forever, right? So every time I'm finding a factor, so I started with k, I found this factor a. Then I looked at a, I found another factor a1. Let's say I look at a1, I find another factor a2, and so on. Now, what do I know? I know that a is bigger than a1, bigger than a2, and so on. Okay. Now, I cannot have an infinite chain of decreasing natural numbers. So this chain has to be finite. It has to end at some point. But how does it end? It ends only when one of my AIs is actually a prime number, right? Because that's basically how my algorithm worked. Every time I said, look at this factor AI that I have right now, it's either a prime number, in which case I found a new prime number, or if it's not a prime number, I keep factorizing it, right? Because I cannot keep factorizing it forever, it means that at some point, I will have to get to an AI that is a prime number, okay? And that's a prime number that was not in my list. And this contradiction shows that there are infinitely many prime numbers, because the contradiction resulted from the assumption that there are only finitely many prime numbers. Okay, great. Let me show you another example. So this is, let's say, problem 4. Well, actually, this one has a name, and we're going to see it a lot. It's the pigeonhole principle. And well, basically it says that if I have a number of holes and I want to put pigeons into them, and if I have more pigeons than holes, there's at least one hole that will get 2 pigeons only. Okay. So if we have n, well, instead of hole, I don't know what to say. Let's just say we have n holes and n plus 1 pigeons. are put in these holes, then there exists a hole with at least 2 pigeons. Okay, so in general, if I have n+1 items and I somehow divide them into n sets or n groups, then at least one of these groups will have to have 2 items or more. Okay. Now, you might think this is very trivial, right? How can we even prove this? But we can prove it because we're not going to add another axiom just for the pigeonhole principle. We already have 5 axioms and we're very happy with our axioms. Okay, so how are we going to prove this? Well, let's prove it by induction, and let's do induction on this number n. So I'm going to do a proof by induction. But here's the part where things get a little bit weird. So what happens if n is 0? Just doesn't make any sense, right? So I have to say this only for n's that are greater than or equal to 1. But that's fine. That just means that the base case of my induction should not start from 0, it should start from 1. Okay. So my base case is that I have 1 hole and I have 2 pigeons. And of course, both of these pigeons have to go to that same hole, and that hole has at least 2 pigeons. So base case, very trivial. Base case n equal to 1, we just checked it. Okay. Now let's do the induction step. So in the induction step, I'm going to assume that this holds for n, and I want to prove it for n+1. Okay. So just imagine this. Imagine that I have n+1 holes. So hole number 1, hole number 2, hole number 3, so on, n+1. And now I have n+2 pigeons, right? So I'm just going to look at the very last hole here. I'm going to look at this one. And I'm going to ask how many pigeons am I going to put into this hole n+1. Now, if I put 2 pigeons or more, then what I wanted to prove is already done because this is a hole that has at least 2 pigeons. So the interesting cases are the cases where I have put 0 or 1 pigeons here. Okay, so if I don't put any pigeons here, then I have n+2 remaining pigeons, and I only have n holes to put them in, right? Kill one of the pigeons. Now I have n+1 pigeons, and I have n holes. And now I can use the assumption that for n holes, if I have n+1 pigeons, at least 2 pigeons are going to be in the same. Okay. Now, the other case is that I have exactly 1 pigeon here. In this case, we don't have to kill it. So for the rest of this, I have n holes and n+1 pigeons again. And again, by the induction assumption, I can say that, well, at least there's going to be at least 1 hole that has both of that has 2 pigeons or more. Okay. So this is how we prove the pigeonhole principle using induction. Okay. Let me see. Let's now do some non-examples, some things that are actually not correct. So you see, when we're doing induction, we said it's very important that we verify 2 things. We have to verify our base case or the induction basis, And we have to also verify the inductive step. We have to verify that whenever phi n holds, the n plus 1 also holds. Okay. So let's see what happens if we forget to do one of these steps. Okay. This is, again, a very famous non-example. I want to prove that all cars are the same color. So at the base case, if I have 0 cars, all these 0 cars are the same color. Okay. I can also talk about 1 as my base case. I can say if I have 1 car, it's of the same color. We're assuming we're working in a universe where cars cannot have more than 1 color at the same time. So if I have 1 car, that 1 car has only 1 color, of course. So the base case seems to be very easy. The base case holds for n equal to 1. Okay. Basically, what is it that I'm proving using induction here? I'm proving that for every n cars, all of them will have the same color. Okay. And that would mean that all cars have the same color. So the way I'm introducing a variable in here is that I'm saying, let's look at the number of cars. So this is what I'm proving for every n, every set of n cars have the same color. And well, again, it's easy to prove it for n equal to 1. Now let's do the induction step. Let's say that it holds for n, and let's prove it for n plus 1. So let's say I have n plus 1 cars. And because I'm not great at drawing, let's say these are my cars. So this is car number 1, car number 2, 3, so on, n, and n plus 1. Okay. So I can use my induction hypothesis, and my induction hypothesis says that every n cars have the same color, right? So that's what I can use to prove that every n plus 1 cars have the same color. But every n cars have the same color. So let's just look at these first n cars, and they all have the same color, right? That's my induction hypothesis. Now, let's kick out car number 1, and let's look at cars number 2 to n plus 1, right? They also all have the same color. Now, these 2 colors cannot be different colors. So all the n plus 1 cars have the same color. Okay. So we proved by induction that for every n, every set of n cars have the same color. What's wrong with this proof?
No, the cars don't have.
Yes, exactly. So the problem here is, let's go back to what we have to prove in our induction. We have to prove that the base case holds, and then we have to prove that for every n, if I have phi of n, then I will also have phi of n plus 1. Okay. Now, again, we can start at 0 or start at 1. That's a choice that you can make, or you can also start at 7 if you like to. And then this would be for every n greater than or equal to 7. Phi of n should give us phi of n plus 1. But what did I prove here? If you look at this proof, it doesn't work when n is 1. Because if n is 1, I just have car number 1 and car number 2. And I'm saying that the first n cars are the same color, fine. And then I'm saying the last n cars are the same color, that's also fine. But then the part that says these 2 should be the same color, that doesn't work anymore, right? So you see, the problem here was that when we were doing this proof by picture, we were adding some assumption without actually realizing it. And the assumption we were adding was that n is at least 2. And I don't have that assumption. So the things that I had to prove in this case was that for my base case, let's say if I call this phi of n, for my base case, I had to prove phi of 1. And then for my induction step, I had to prove that for every n that is greater than or equal to 1, phi of n implies phi of n plus 1. But this is not what I proved. What I proved was for every n that was greater than or equal to 2, phi of n implies phi of n plus 1. And I mean, that makes sense. If you think about it, if every two cars were the same color, then all cars would be the same color. Okay. Now, here's another one. I'm not going to even write this one because this is a little bit too stupid. We can prove by induction that everyone is bald. So here's the proof by induction. I prove that if you have exactly n threads of hair on your head, you're bald, okay, for every n. So the proof is this. If you have no hair at all, if n is 0, you're definitely bald, right? Now, suppose that you're bald if you have n strands of hair. If I give you just one more hair and you have n plus 1 now, will you stop being bald? No, you're still bald. So no matter how much hair you have, you're bald. Now, the problem with that is actually a little bit different. It's because we don't have a well-defined mathematical definition of baldness, right? So you have to be careful about what you're doing in your arguments, especially when you're using the induction. Okay, but let's go back to some real examples. So how many problems did we solve? This was problem 4. Let's do problem 5. Okay. Here's the thing. Suppose that we have a tournament, and in this tournament, we have n players. So n players take part in a tournament. And let's say that every player plays with every other player. Okay. You can imagine that this is a game that doesn't have any draws. So we're not playing chess, we're playing, I don't know, rock, paper, scissors also has draws. We're playing a game that doesn't have any draws. So every player plays against every other player. And every game has a winner, exactly one winner, of course. We cannot be in a situation where both of them. Okay. Now, what I want you to prove is that I can just put all the players in some particular order such that everyone has won against the player to their left and lost to the player to their right. Okay. So prove that there exists, well, we call this a permutation of the players, basically an ordering of the players. Let's call this P1, P2 to Pn, such that for every I that is between 1 and n minus 1, Pi has lost to Pi plus 1. Okay. And this is no matter how the games went. So I have n players, they play the games, I see the results of the games, and based on the results, I want to somehow sort them like this, P1 to Pn, so that P1 has lost to P2, P2 has lost to P3, and so on. prove that this is always possible. I really like this part of my job. I can just stand here and look at you while you prove this. Okay, let's prove it by induction. And we're doing induction on n. And we're going to start our base case from 1. Okay, so my base case, actually, I can also start with 0 here, because if I have no players, I have one way of putting the players in order, and that's that I have the empty order. Right. But if I have only one player, I can just use that one player as my permutation. So if I have one player, and let's say the players are numbered from 1 to n, then the sequence 1 is an answer. Okay, that's my base case. Now I want to do my induction step. So I'm going to assume that this is possible for n players. I want to prove that it is also possible for n plus 1 players. Okay. Now, so this is the induction step. I have n plus 1 players. Let's take out player n plus 1 and just look at the first n players. I know that there is a way to put them in order such that each player has lost to the next one. Okay, so consider an ordering of the first n players. An ordering, let's call it P1, P2 to Pn of the first n players of 1, 2 to n. Okay. I want to add player n plus 1 somewhere in this ordering. Where can I add this new player? Well, I just check. Did n plus 1 lose to this last player here? Or did n plus 1 win against this last player here? If n plus 1 won against Pn, then I can just add n plus 1 right here. Right? And everything would work out because P1 has lost to P2, P2 has lost to P3, so on to Pn, and then Pn has lost to n plus 1. Okay. But let's say that this was not the case. Let's say that Pn won against n plus 1. So I just go one step before. I look at Pn minus 1. So this is, let's say I have P1, P2, P3, so on. And on this side, I have Pn minus 1, Pn minus 2. So I checked, and this new player, the last player, player n plus 1, has not won against the last player of my order. So I just check with the previous one. I check, can I add my player n plus 1 here? Okay, because player n plus 1 has lost to Pn, I just have to check whether player n plus 1 has won against Pn minus 1. And if that's the case, I can insert it. Well, I keep doing the same thing until I get to the beginning of my list. And if I find somewhere at some point where I can insert a new player, I would be happy. But let's say that I didn't find anywhere to insert this new player. This means that the new player that I wanted to insert has actually lost to everyone else. Right? But if that's the case, then I can just add them at the beginning. So in any case, I could find an ordering of my n plus 1 players that satisfies the requirement that everyone has lost to the player to the right. Okay. So this shows by induction that this is always possible. Now, at some point in this course, we're going to do graph theory. And basically what this is saying is that every tournament has a path of length n-1. Okay. Now, let's go back and let's see why these things are actually equivalent. So why is it that the well-ordering principle, the infinite descent principle, and mathematical induction are actually saying the same thing? Okay. So in order to prove this, I have to show that somehow each one of these statements, the mathematical induction statement, the well-ordering and infinite descent, implies the other ones. Okay. So let's do this. I have infinite descent. I have induction. And I have well-ordering. Okay. I want to find the implications between these. Which ones are easier, do you think? So I think I can do this one pretty easily. So basically, let's prove this theorem. Let's prove that if we have the principle of infinite descent, then we have the principle of well-ordering. Okay. So this is part one. Let's call this one. I want to prove, assuming infinite descent, that well-ordering holds. Okay. What was infinite descent? Infinite descent just said that I cannot have an infinite sequence of natural numbers that is always decreasing. What was well-ordering? Well-ordering was that every non-empty subset of natural numbers has a smallest element. So I want to prove well-ordering. And I say, suppose this is not the case. Again, I'm going to do proof by contradiction. Suppose well-ordering does not hold. Okay, so let A subset of natural numbers be a non-empty set without minimum, without a smallest element. Okay. So this is what it means for well-ordering to not hold. It means that there exists some subset of natural numbers that doesn't have a smallest element. I want to get a contradiction with this using infinite descent. Okay. How can I do this? Well, I say A is non-empty, so I can pick some element of A, right? Just pick any element, pick any A0 in A. Okay. Now, my set big A did not have the smallest element. So A0 is not the smallest element. So there is something in A that is smaller than A0. Okay. Let's look at the set of all the numbers in A that are smaller than A0. Okay. So let's define something like this. Let's say big A0 is the set of all the numbers in A, so all A primes in A, such that A prime is less than A0. Okay. What do I know about this big A0, about this set? I know that it's non-empty, because if it's empty, then A0 would be the smallest element of A. But I assume that A doesn't have the smallest element. So A0 is non-empty. I also know that A0 does not have the smallest element, because if A0 has the smallest element, that would also be the smallest element of A. And I know that A doesn't have the smallest element. So A0 is a set that is non-empty and doesn't have a smallest element. Just pick one element of A0. Okay. So now I say pick any A1 in A0. Okay. Now do the exact same thing. Say that I say the set A1 is the set of all the numbers that are less than A. Now I can continue the same thing. I can basically do the same argument as before. I can say this set doesn't have a smallest element and it's also not empty. So pick one element of this set. And I can do it forever. So basically, every step is that pick any AI plus 1 that is in big A of I, and then define big A of I plus 1 as all the numbers that are smaller than AI. Okay. So this gives me a sequence. I now have this sequence A0, A1, A2, so on, and it's an infinite sequence, right? But it's also a decreasing sequence because by definition, I picked A1 from this set, but this was the set of all the numbers in A that were smaller than A0. So A1 has to be smaller than A0. And then similarly, A2 is smaller than A1, and so on. So this is like this, and it goes forever. And this is a contradiction because I said that I'm assuming I cannot have infinite descent. So assuming infinite descent, I could prove well ordering. Okay. Now, let's do this. Let's say that I have well ordering and I want to prove induction. Let's call this 2. So what do I want to say? What was induction? Induction was that if I have a set, let's say K of natural numbers, and if K includes 0, and whenever it includes a number n, it also includes n plus 1, then K includes all the numbers, right? That's what induction is. So I want to prove that, but I have well ordering. Okay, so here's the thing. Let's say I consider a set K, let K be a set of natural numbers. And let's say that it satisfies those two conditions that I had in induction. So 0 is in K, and for every natural number n, if n is in K, then n plus 1 is in K. Okay. I have to prove that K is the set of all natural numbers. Okay. And in order to prove that, I can use well ordering. So look, here I don't have Peano's axioms. I don't have the last axiom of Peano because that's what I want to prove, right? So basically, my point is that I want to eventually show that all three of these things are saying the same thing. So I want to say that as my fifth axiom, instead of having induction, I could just put well ordering, or I could just put infinite descent, right? That's what I want to prove. So here I cannot use that axiom, but I can use my other axioms, and I can use well ordering. So I want to show that well ordering implies induction. So I have this set K, 0 is in K, and whenever n is in K, n plus 1 is also in K. Okay. So I want to prove that K is n. I want to prove that K is the set of all natural numbers n. Okay. Again, I do proof by contradiction. I say, suppose K is not equal to n. Okay. So suppose K is not equal to n. If K is not equal to n, it means that there is a natural number that is not in K, right? So I can basically take the difference of the two sets. So I'm going to define a new set. Let's call it A. I define the set A as n minus K. So all the natural numbers that are not in my set K. Okay. Now, because I'm assuming that K is not equal to n, that's equivalent to saying that I'm assuming this set A is not empty. Okay, so A is not empty. if A is not empty, A must have a smallest element. Because remember, this is what we're proving. We can use well ordering here, and well ordering says that any set that is non-empty has the smallest element. So I can say let M be the smallest element of A. Do you see the contradiction already? So what happens if I look at M minus 1? Right? Okay. So look, this M, it's definitely not 0 because 0 is in K. Right? So this M is a number where M minus 1 exists. Or if I want to use the language of Peano, M is the successor of some other number. Let's call that other number T. Okay? Because this is the case, and because M is the smallest element of A, then this T has to be in K. But if T is in K, then T plus 1 is also in K, or again, successor of T is in K. So, but that contradicts with M being in A, because A is the set of all the numbers that are not in. This contradiction shows that if you have well ordering, you also have induction. Okay, so what have I shown so far? I have shown that infinite descent implies well ordering, and well ordering implies induction. Now, I can also go in the other direction. I can try to say, well, let's also prove that induction implies well ordering, or let's also prove that well ordering implies infinite descent. Or I can just close this cycle. If I just prove that induction implies infinite descent, then that's enough, and I have proven that all of these three are equivalent. But I don't have time to prove that, so we'll see that proof next week.